Muons are fundamental particles like electron. These are unstable particles with a very short lifetime of about 2.2 microsecond. With this lifetime, it can travel up to 0.66 kilometer. However, experiment shows it traveled all the way through the atmosphere and reaches the detector, and which means it travels more than travel. How does it travel more than 15 to 30 kilometer? We will understand this in this video, and this is very basic question asked in many PhD interviews, and this simple experimental observation will help us to understand uh, the concept length contraction and time dilation. So to understand this, we will need some basic idea of about what are cosmic muons, where are they produced, what is their lifetime, how far can they travel, and how we detect how they reach the detector. We will understand this. So what are cosmic muons? First, we need to know what is cosmic ray. These are mostly energetic protons coming from outer space constantly. As this cosmic ray or proton enters the atmosphere, it interacts with the nucleus in the present in the atmosphere and produces secondary particles like pions, kaons, etc. These pions further decays into muon, as you see an example. Um, and This muon, these are heavy and quite unstable and decays to electron type neutrino and muon type neutrino and so on. This decay is statistical and completely random process, and the lifetime of the decay or decay time follows a exponential distribution with a mean time of 2.2 microsecond. And if we do a simple calculation, how far it can travel before it decays, if we take the upper limit close to speed of these are most energetic particle and travels at the speed close to speed of light. If we take a simple speed upper is equal to speed of light, then we will obtain the length it traveled is around approximately 0.66 kilometer. That means our the distance between the point where it produced and the detector is more than 14 to 30 kilometer, and it can travel only 0.66 kilometer. That means it will decay before it reaches the detector. However, there are experiments which suggest that we detect more muon events than expected, or the muon reaches the detector. Now, why? How this muon reaches the detector? Let me introduce what is time dilation in special theory of relativity. Let's say we have two observer A and B. Observer A, let's say, moving at a velocity or velocity v with respect to observer B. Let's say initially they are both are at rest, so the time, let's say at t is equal to 0 and at t is equal to 0, A started moving at a velocity v with respect to B. After, let's say, some time, since time is relative, let's say observer A reads a time t1 and observer B reads a time in his clock t2. According to Einstein, since A is moving with a velocity v with respect to B, so it clocks slows down with compared to B. So the time t2 would be t1 times gamma, where gamma is the Lorentz factor, and its value is greater than equal to 1. And if we use, you see the moving observer, whatever time it, the time, the rest observer is gamma times the time in the moving observer. So we will understand it in better way with this example of muon case. Let's say muon is our observer A, which is moving at a velocity v with respect to our observer B, which is the detector on the surface of Earth. And T0, let's say T0 is the muon lifetime in its rest frame. That means in muon's frame, its lifetime is equal to T0, which is equal to 2.2 microsecond. The time, this time, T0 time, lifetime, will observed by the detector is the time the detector will, the lifetime in the detector's frame of reference is, as I mentioned previous slide, is gamma times T0, where T0, where gamma is the Lorentz factor. Let me give you one example and see how far that can travel if we include the effect of, or the effect of time dilation in our calculation. So let's say, as you know, mean lifetime is 2.2 microsecond. Velocity is 0.9999 times speed of light. And gamma factor, if we compute, it turns out to be 70.7. So so in muon's frame, its lifetime is 2.2 microsecond. It in its frame, it will decay after 2.2 microsecond. However, the observer, since time is relative, the observer on Earth, or the detector, will observe decay of this muon after 70.7 times 2.2 microsecond. That means gamma times 2.2 microsecond. And if we include this with, we will obtain the length traveled by the muon in the detector's frame of reference is around approximately 46.6 kilometer. And can you compare, you see, if we include no time if there are no time dilation concept, then it can travel only up to 0.66 kilometer. However, if we include this, and we detect these muons, this is a very strong experimental evidence that validates the concept of time dilation and length contraction. And this is very important question that also asked in many PhD interviews. Even I was asked in a PhD interview at Niger. Thanks for watching.